This is an actual exam 1 I gave in statistics class in SUNY Maritime College. I put in like 3 sub-problems to make it more complete so that if you're using this video for future exams, it will be better. The first question here is regarding 221 data points of 6th graders 1 mile run. And the first question is asking which class should 7 minutes and 59.4 seconds belong to? Well, you need to convert 7 minutes into seconds because everything here is in seconds. So you have to multiply 60 to 7 and then add the 59.4. 7 times 60 is 420, so you can see that this is 479.4. And the problem here is that 479.4 is slightly bigger than 479 and less than 480, so it's kind of in between this number and that number. So at first you might be puzzled where this should fit, but you see when you write the lower class limit and upper class limit, then anything that's outside could belong still to here if you round it to the nearest number. See, 479.4 is closer to 479 than 480, right? So 479.4 actually belongs to this class. Now that naturally leads us to the second question, where's the class boundaries for the 540 through 599 second class? Well, that's because we saw that 479.4 should round down to 479. So despite the fact that the lower class limit is 540, the number 539.5 could still be classified as this class, and it could go all the way up till 599.5, and that gives you 599.5 itself will be categorized into 600, but anything slightly smaller than 599.5 would be categorized as this class, so that's why you include up till 0.5. Okay, so that's the class boundary. Now, is the above data skewed to the left, skewed to the right, or not skewed at all? To answer that, you need to think about the histogram. See, because it's 9, so let me draw it here. So you have 9, and then it shoots up to 91, and it comes down to 75, and it goes down to 32, and then 10, and then 4. If you actually drew the histogram carefully, you're going to get such a graph, and you can see that the tail is extended to the right. In that case, we say it's skewed to the right. This is a little confusing, but that's how people commonly call this. So we have to follow the common idioms in the statistics. Some people might think, well, the head of this data is to the left, so isn't this skewed left? No. You always look at the tail, or I like to say the feet of this is extended to the right. So this will be skewed to the right. What is the modal class? The modal class is the class with the highest frequency, and you can see here it's 91. 91 is bigger than anything else, so that's the modal class. Which class contains the median? Well, median is the number that you would get in the middle if you were to put all the raw scores from the smallest to the largest, right? Since there are 221 data points, if you take half of it, that's 110.5, and that rounds to 111. So the 111th number would be the median number. And because 9 plus 91 gives you 100, 111th number would fall in as one of these 75 numbers. Therefore, the median would belong in here. So this is also called the median class. So the class containing the median is called the median class. Compute the approximate average running time from the table. Write down what you're plugging into your calculator. Okay, the problem here is that we don't have access to the actual raw data, so we need to somehow make an estimation of values in each of these classes. And the best way to approximate would be to take the midpoint of the class limits. So because we don't know what running times are actually included in this class, we don't know the 9 numbers, we're just going to say that all those are actually the midpoints of these 2 numbers. So you want to calculate the midpoint by adding these 2 and dividing by 2. Okay, so I'm going to use TI-84 calculator. Let me turn it on. And 360 plus 419, and then divide that by divide this by 2, and that's going to be 389.5. So that's 389.5 is the midpoint. And then I have to do it for all of these, but if you look at the data, it's always 60. So the class width is 60, right? So this difference between these two are called class width. The class width is 60, so you can just start adding 60 to get all the other numbers, so that you don't have to do all the calculation. Okay, 60 plus 6 plus 38 is 449.5. 44 plus 6 would be 50, and the 6 added, that would be 56. 56 plus 6 would be 62, and then this would be 6. You get 689.5. However, you have to be careful in the last one. See, sometimes the class width are different in the last class, so you might have to actually check that by adding 660 plus 719 and divide it by 2. No, don't do that yet. I'll just divide by 1. Now divide by 2, and you get 689.5, which agrees with this, so everything's good. Okay. So these are the numbers, and then what I need to do is, since you have 9 389.5s and 91 449.5s, you just multiply the frequency by these numbers, you add them up, and whatever number you get, you divide by 221 data points to get the average. That's how you would approximate the average just from the frequency table. So let's do that. Move it here. So you have 389.5 times 9, and then plus 449.5 times 91, then plus 509.5 times 75, plus 569.5 times 32, plus 629.5 times 10, and then plus 689.5 times, actually not plus, I'll change that, and it says a times 4, and then enter, and you divide this by 221. That's going to give you 497.28. So 497.28, and you have to write all the calculations you did. So you might as well just copy these numbers down here as paste as numbers, delete all this, and then make it as multiplication, addition. Okay. And then times 75 plus, that should be times 32, 625 times 10 plus this one here times 4, and then everything should be divided by 221, and that gives you 497.28. So that's the average. Okay, next question. A survey of college students looked at how many credits they are taking, how much time they're spending on doing homework each day, which subject they worked the longest on. It also surveyed their emotional well-being, with the choices being A, I seldom feel sad, B, I feel upset about things, C, I feel that I do things wrong a lot, D, I feel unhappy a lot of time. Okay, so first question is, what is a qualitative nominal data? Well, qualitative is anything you can't put numbers on it, so it's actually easier to talk about quantitative. Quantitative are like credit hours, right? And how much time they spend on doing homework. These are 1 and 2 are both credit hours, but credits, they go by integers, right? And then these the time that you spend doing homework each day could be like 1 hour and 30 minutes or 1 hour and 20 minutes. So a continuous data, continuous means unbroken, right? Continuous means that if you have 2 numbers, 3 and 5, can you have 4? Or if you have 3 and 4, can you have 3.5? If you have 3 and 3.5, can you have 3.25? If there's always a possibility for a value to be between any of the 2 chosen values, that's what we call continuous data, because you can have decimals. On the other hand, discrete data is if the data cannot have in-between values. So, for example, if a data can only be integers, you can't have 4.5. You can't have a value between 4 and 5. 4.5 is not allowed. So that's why for quantitative discrete data, this will be 1, whereas for the quantitative continuous data, this would be 2. Okay, so quantitative discrete 1, quantitative continuous 2. Now let's move on to qualitative. These 3 and 4, they're both something that cannot be put in numbers, right? The subject may have a class number, but that number doesn't mean anything. So this is a qualitative data, as well as the emotional well-being, that will be qualitative as well. Now, however, the subject just has a name, so that's just the nominal data. On the other hand, the emotional well-being, although this is not something that you can put numbers in, but you can kind of put order of things. So like A would be a person not being in depression, but people who said D could be in depression, right? So this is more of an ordinal data. So it's a qualitative, but you can order them in certain order. In that case, it's a qualitative ordinal data. If the survey was done in various states, including community colleges, private liberal arts colleges, and public four-year colleges, and if you want to find the right proportion of race, ethnicity, gender, and all that, what type of sampling method is this? This is called stratified sampling method. On the other hand, if the survey was done in only one college, and let's say you just went to one dorm and collected all the data from there, and that kind of method would be cluster sampling. So, which is not desired, but sometimes you don't have the money to do a stratified sampling, so you might end up with a cluster sampling. Number 3, biologists caught 10 raccoons to tag and vaccinate for rabies. Their size was measured and published as a stem and leaf plot. Okay, so stem and leaf means you say 2 means 22, 2, 3 means 23. So you should be able to write all the numbers down explicitly from a stem and leaf. So since the instruction here says 1 and then leaf 9 means 19, so you should really say 19, and there's the 22, 23, 25. So let's just write all of them down. 22, 23, 25, 25, 27, 27, 28. And then you have the 30 and 32. Now you want to find the median. Because this is an even number, the median will be right between these two. So you take the average of these two, and average of 25 and 27 would be, this would be 26. So 26 centimeters will be the median size. Find the mean and standard deviation of the captured raccoons. Write the formulas needed for these calculations as well. Okay, well, probably the best way to do this is to just put all those numbers in a table and click stat. That's faster, but you also have to write the formulas for these calculations. That's because you should know how they were obtained, not just punching them into the calculator. So although the quicker way would be just to use the table, you can certainly do that and then write the formulas, but let me just show you how to do this on a calculator. So you do 19 plus 22 plus 23 plus 25 plus 25 plus 27 plus 27 plus 28 plus 30 plus 32, and enter. You get 258, and then because there are 10 items, you end up with 25.8. Okay, so what you need to do is you just take all of these, you add them up, and then you divide it by 10, which is 25.8. So that's the median. Now the next thing that you have to do is for the standard deviation, you first have to find the variance, and the variance is defined as the difference from the item to this thing squared. So what you need is 19 minus 25.8 squared plus it'll be 22, and then plus the next one is 23 plus 23 25 25, and then the next numbers are 27, so let's just copy this one, 27, and then 28, 30, and then 32 is the final one. So you add the square of the difference between that item to the mean, and then you, after you add everything, you divide it by the number 10. Okay, so that's the variance, and after that, the standard deviation will be the square root of this. So let's actually do that. Actually, let's see. 25.8 minus 19 will be 6.8. So let's put 6.8 squared. Again, there's an easier way if you use a calculator. This difference will be 3.8. Squared, and then plus plus 3.8. Oh no, sorry, this would be 2.8. 2.8 squared, and then another 2.8 squared, oh, I think I made a mistake here. There's a 2355, so I put 23 twice, so let me delete that. Okay, so in that case it will be plus 0.8 squared, and then plus 0.8 squared, plus then 27 and 25.8, that's 1.2 difference. 1.2 squared plus 1.2 squared. And then this will be 2.2 squared. Uh, 4.2 squared. Okay. And then plus finally this will be 6.2 squared. Okay, so you have 196.49, so we'll just put it as 196.5. So this would be equal to 196.5, and then divided by 10, and that will be 19.65. And after that, you have to take the square root of that, so I take the square root of 19.65, enter, and that gives you 4.43. So the standard deviation would be sigma equals to 4.43. Find the best approximation of the standard deviation of all the raccoons in the region. Now, you might think this is the exact same thing as this, but there is something called the Bessel's approximation, which says that instead of dividing by 10, you have to divide by 10 minus 1 for the populations. And the reason is this. When we did this variance, we subtracted by the mean value of the sample, right? And the mean value of the sample has the tendency to be closer to the data you selected than the actual mean from the entire population. So if we use the mean value from the entire population, what we computed can be taken as the standard deviation of the all raccoons in the region, but because we don't have access to that mean, we can only say that we're using some approximation. And there's something called Bessel's approximation, which says, well, in that case, because the mean from the population will make this larger, you have to divide by something slightly less than 10. So instead of dividing by 10, you have to subtract 1 from the 10. That's called the Bessel's approximation. So by Bessel's approximation, you have to take this 196.5 and divide it by 9. And let's see, 196.5 divided by, oops, that's not what I wanted. Divided by 9, and that gives you 21.8. Okay. And then you take the square root of that. You take the square root of this number, 21.83. You get 4.67. So standard deviation would be 4.67. Oh, by the way, if you put this into a table, this is what's written as S of X, which is the sample standard deviation, okay? And that's 4.43, whereas the sigma of your sample would be 4.67. So if you're using the table, you can get this a lot quicker that way. But because it says to write the formulas, you should be able to write the formulas. Let me see. Oh, no, sorry, I got this backwards, sorry. This should be sigma, and that should be Sx. Because you're considering your thing as a sample, okay? So you're using the sample to predict the entire standard deviation. So this Sx is the bigger number. So whichever is the bigger number will be the standard deviation of the best approximation for the entire population, whereas the smaller number is the standard deviation for your own sample. Okay, in a region, 43% of all raccoons are infected with rabies. If biologists caught 10 raccoons, what is the probability that exactly 8 out of 10 were infected with rabies? Write your answer rounded to 4 decimal places. Okay, so for this question, you should think of this as a probability of one raccoon being infected with rabies, right? And you're trying to repeat that for 10 raccoons, so this is actually a binomial distribution. So it's very important that you know that this is a binomial distribution problem. And if you don't know that, you wouldn't be able to solve this, okay? So for this, once you know that it's a binomial distribution and you caught 10 raccoons and you're trying to see what's the probability that 8 out of 10 were infected with rabies, what you do is you say, oh, the probability is 0.4843, and because Q is 1 minus P, that will give you 0.57 as Q, and you need the Q if it's a binomial distribution because the formula requires that. And also N is equal to 10 because you're collecting 10 raccoons. You're repeating that for 10 times. So once you have this, then you can use the calculator to find out the probability that X is equal to 8. And for that, what you need to do is you do second vars, and you want to find the binom PDF, and you have total of 10 trials, and p-value is 0.43, and then the x value you want is 8, so you paste that, and that gives you 0.01708. 0.1708. Okay. It says rounded to 4 decimal places, so I guess if you round it's this. So is finding 8 rabbit raccoons out of 10 unusual? It's very unusual because it can only happen in less than 2% of time. So yes, because it can happen for only 1.71% of time. And what is the expected number of raccoons with rabies among 10 raccoons? Well, if you multiply, so the formula is that the average in a binomial distribution is NP, and because I have 10 and then P is 0.43, that's 4.3 raccoons. Okay. Yeah. So you'll be getting you expect to get 4 raccoons usually, or maybe sometimes 5, but it's saying 8 is too much. So this kind of information can be used to say that, oh, we thought it was 43%, but something's not right. Maybe there's a rabies going around the entire forest by some vector, and we have to figure this out again. Something's not right, or something's going bad, right? So that's what this problem can tell you. The charity organization Overcome Cancer is selling lottery ticket door to door. 2,000 tickets are sold, among which 100 tickets had $100 award. So there's 100 out of 2,000 that you can get a $100 award, and that's pretty nice, right? So let's see what that is. 100 out of 2,000. That's 0.05 or 5%. 5%. And oh, not here. Sorry. That's the case when you have $100, right? Okay. And on the other hand, there's 200 tickets for $20 award. So this is twice as much as this. So it'd be twice the percentage. So 10%. There's a 10% chance that you're going to get the $20. And 200 tickets had $20 award. No, 300 tickets had $10 award. So it's 3 times this one. So that's going to be 0.15, which is like 15%. Now, the rest has no award. So if it's not one of these, you get $0. And because probabilities have to add up to 1, adding these 3 gives you 0.3, so this one must be 0.7. So 70% of the time, you're not going to get any award, okay? So that's how you do it, okay? So for example, you do 100 divided by 2,000, and you get 0.05. Okay. What's the expected award money of a random ticket? Well, the award money would be, you're trying to find the expectation value of this x, right? And the expectation value is computed by multiplying the value times the probability. So this will be like 0 times 0.7 plus 10 times 0.15 plus 20 times 0.1 plus 100 times 0.05. And let's use your calculator. The first one is 0, so I'm not going to do that. 10 times 0.15 would be 1.5, plus 20 times 0.1 would be 2, plus 100 times 0.05 would be 5. So adding them, it will give you 8.5. So that's the expected award money of a random ticket. It's $8.5, okay? And if the lottery ticket was sold for $10 and you bought 1 ticket, what is the expected loss? Well, you've spent $10, but on the average, you'll only recover $8.5. So 10 minus 8.5, what's that? That's 1.5, right? So that you're actually going to have, you will lose $1.50 if you buy 1 ticket, okay? And the charity organization will actually gain $1.50 per ticket, assuming they sold all the 2,000 tickets. Okay, the Shih Tzu dog breed has average lifespan of 14.1 years, and a standard deviation of 2.3 years. This data is normally distributed, and so the question is, if a child bought a newborn Shih Tzu puppy today, what is the probability that the dog will still be living after 15 years? Well, first you have to convert the 15 into z-score. So let's see, z would be 15 minus the average, 14.1, and you divide it by 2.3. And let's see, 0.9 divided by 2.3 would be 0.3913. And in here, what's happening is you have 0.3913 is somewhere here, right? And you're trying to find the probability in this area. Now, what you have to know for standard normal distribution is that the area gives you the probability. That's what distribution functions do, the probability density function. The area gives you the probability. Okay? This is the value that you want, the area. However, on the calculator, in the basic setting, they give you the area. They give you the area from negative infinity up till a certain point that you give. So the upper bound. And because this is given and you're trying to find this, you have to use the fact that the entire thing is 1. And the better drawing would be doing the following. You can say this is equal to the entire thing shaded minus this side somewhere here, right? And if you subtract this minus this, you're going to get P, and everything under is 1 because probability of everything is 1. Then to find this one, to find 0.3913 like that, you need to use the calculator norm CDF function. Okay, so you have to go to second vars, normal CDF, and don't change anything, just put the upper as 0.3913, enter, and that gives you 0.6522, and 1 minus 0.6522 gives you 0.3478. Okay, so that's so you end up saying that P is 1 minus 6522, and that's equal to 0.3478. Okay, what percentage of Shih Tzu dogs live between 14 to 16 years? Well, we have to find the z-score for the other cases as well. So let's calculate that. 16 has the z-score of 1.9 divided by 2.3, so it's 0.8260. Also, the z-score for 14 would be negative 0.1 divided by 2.3, so it would be negative 0.0435. I don't know what's happening. I'll just put this here. 0.0435. Okay. So these are the z-scores, and what it means is we want to find the area between here, let's say here's 0.435. It's actually there should be a minus, sorry. Should be a minus. So let's move it slightly to the left of 0. And then 0.826 is somewhere here. And we're trying to find the area of this. And if you have area captured between two places, what you need to do is you have to make it as a subtraction between 0.8260, this, minus this one would be negative 0.0435. Okay. And therefore you would have you can clear everything. Okay. So again, you want to do second vars, normal CDF, and put 0.8260, enter, and that's 0.755 or 0.756, and then do second vars, normal CDF, and then put negative 0.0435, enter, and you have to subtract the two. So you might want to say point equals to 0.7, keep forgetting, 7956 minus the second number is 0.4827, 0.4827, and what is it, 0.7956 minus 0.4827, 0.3129. So 31.29% is the probability. Okay, this time you have to find this X, which says only 1% of Shih Tzu breeds will live beyond X years. Okay, so you can imagine that there's this right tail, very small portion, where this area is just 0.01. Now, to find this, you should really think of this as the critical value of 0.99, because if this small tail is 0.01, then 0.99 would be this much, right? So what you want to do is you want to find this value using this critical, and you do that by using second vars of inverse norm. So area, what I want is 0.99. And what you get is 2.326. So we see that, sorry, I really meant that this 0.99 is the area. So let me raise this portion and really write 0.99 here. So you have 0.99 here, and then we've just found out that the value of the x coordinate is 2.326. So here it's 2.346. And the problem is that this is obtained on the standard normal distribution, right? So we're looking for the age x whose z-score is 2.346. So what you need to do is you're trying to solve for this x minus 14.1 divided by 22.3 as this critical value 2.346. And to do that, you would need to do x equals to, you multiply by 2.3, and then you would need to add 14.1. So you want to do 2.3 times 2.346 plus the average 14.1. So that's 19.5. So you can say that only 1% of Shih Tzu breed will live beyond 19.5 years. So 19 and a half years later, 99% of Shih Tzu breed would die. Okay, here's a similar question. Find the Q3 or the 75th percentile of this data. Same thing, you look for the 75%. So let's just say this somewhere here is like 75%. So in terms of the area, it would be 0.75, right? So you put second vars, inverse norm, 0.75, and that gives you 0.6744. Okay. So we see that this value down here will be 0.6744. Okay, this much. And again, this is your critical number, which is a z-score, so you have to figure out the x whose z-score would be 0.6744. So that's going to say that x is equal to 2.3 times 0.6744 plus 14.1. And that one, let's see, that's 2.3 times 0.6744 plus 14.1, and that gives you 15.65. So that's your Q3. 15 point, or rounded to the 10th of a year. That's what it is. If two Shih Tzu puppies, both less than a week old, were bought, what is the probability that the average of the lifespan of the dogs is 15 years or greater? Okay, you must first find the sample variance with sample size n equals to 2. Okay, so this is like taking a sample size of 2, and if the original one is a normal distribution, then the average of 2 samples is again normally distributed with the same mean, but the sample variance will have to be divided by the 2 as well. So what happens is that if the standard deviation is 2.3, the standard deviation of the sample mean is same as the standard deviation of the original and divided by square root of n, where in our case it's 2.3 divided by square root of 2. And that will be 2.3 divided by square root of 2, which is 1.626. So the new standard deviation is smaller because if you take averages, they don't vary that much as before. Okay, so you have this smaller standard deviation, and therefore now when you take the z-score, you have to take the z-score of the 15 years minus 14.1, and then the sigma will no longer be 2.3 but 1.626. Okay, so let's see, 0.9 divided by 1.626, and that's 0.5535. And because, let me delete this, because you're trying to find something bigger than 15 years, we're looking for 0.5535, and you're shading this part. So again, you have to subtract 1 minus the cumulative distribution function from negative infinity to 0.5535. So let's go to second vars, norm CDF, 0.5535, enter, and you get 0.71. And subtracting from 1 minus 0.71, you end up with 0.29, so the answer will be 29%. There's a 29% chance that they will be, the average lifespan will be 15 years or greater. The ages of the members of a gym have a mean value of 45 years and a standard deviation of 11 years. From Chebyshev's theorem, at least what percentage of gym members are aged between 23 and 67? Well, see, 23 minus 45 divided by 11 gives you negative 22 over 11, which is negative 2. And same thing can be said of 67 minus 45 over 11, and that's positive 2. So we know that 23 x 67 is really, this probability is really probability that you have 45 minus 1, not 1, sorry, 2 times the 11 x, and then 45 plus 2 times 11. And Chebyshev's theorem says that this probability is greater or equals to 1 minus 1 over k squared, where k is this value here. So it's 2 squared. So that would be 1 minus 1/4, which is 0.75. So we know that there's at least 75% chance that the members, at least 75% of the members will be between 23 to 67. However, if you know the shape of the curve and you actually know that it's a bell-shaped curve, then you can say much more. You can say that approximately 95% of the population is between the 2 standard deviation away from the mean, and that's also called 68, 95, 99.7 rule. If you only look for 1 standard deviation below and above the mean, it's 68%, and 95% of the data will fit between above and below 2 sigmas, and 99.7% of the data will fit between below 3 sigma to above 3 sigma from the mean. Okay. Last question. A dice was thrown 600 times and it shows 620 times. So that's a little unusual, because if you usually throw it 600 times, you would expect about 100 times, right? Because I mean, 6 is 1 out of 6 numbers, so 1 out of 6 would be 600 times 1/6, that would be 100, right? So that's a little unusual, and you can say, you have a hunch that that's unusual. This dice is not fair. However, to do this with statistics, you actually have to use the formulas for binomial probability, where it says that the average is NP, whereas the standard deviation is square root of NPQ. And in our case, N is 600, P is 1 out of 6 chance that you get a 6, and Q would be 1 minus 1/6, so that's going to be 5 over 6. So you see that mu is equal to 600 times 1/6, which is 100. Whereas for the sigma, you need to do square root of 600 times 1/6 times 5 over 6. And you can just plug this into the calculator, but I'll just do it as square root of 500 divided by 6. If you multiply, after canceling this 6 with 6, you get 500 over 6. So let's put that into the calculator. 500 divided by 6 is this. So if you take the square root of 83.33, you get 9.12. So you get 9.12. Since 20 is below 100 minus twice of 100 minus 2 times the 9.12, what's that? 100 minus 2 times 9.12 would be 81.76. This would be unusual. And that's it. That's all the questions. Thank you for listening.